Assalamualaikum and hi everyone. So my name is Muhammad Fikri bin Muhammad. My matrix number is 208257. So today my group want to present about the application of function in biochemical engineering. So next slide one. So today topics is basically about how we want to calculate the rate of growth of microorganism. So first thing first, I want to talk about theory and the purpose of the theory that we choose. So the theory is monod equation. So basically, monod equation is a mathematical model for the growth of microorganism. It is related to growth of microorganism to the concentration of a limiting nutrients. And the monod equation has the same form as the Michaelis-Menten equation, but differs in that it is empirical, while Michaelis-Menten equation based on theoretical consideration. So as we know, empirical is a meaning that the equation is made based on experiment and experience. Okay, so we can see the equation, which is mu equal to mu max times S over Ks plus S, where mu is the specific growth rate of the microorganism. Mu max is the maximum specific growth rate of the microorganism, while S is the concentration of the limiting substrate for growth. And Ks is actually a constant. Okay, it is the half velocity constant, which is the value of S when mu over mu max equal to 0.5. Okay, so this is the theory we choose. So next. So for better understanding, I would like to show all of you the graph. Okay, so based on the graph, we can see mu rises rapidly as S increase, then mu slowly decrease until reaches a maximum mu max. At this point, the growth rate is independent. So from this graph, we can find mu max. Okay, so we can see when we take the value of mu times to Ks, we can get mu max over 2. Okay, so from the graph, we can see we can get half of the mu max, which is mu max over 2.
Okay, so for the question, during the growth of E. coli in a batch reactor, the pattern can be remodeled using a monod equation. So the question asks us to show how the time required to reach the maximum population of cells can be estimated, which means we need to show them without substituting the value, and then the question gives us some information to substitute, which is the XO, exponential growth, the start of the exponential growth, the SO, which is the essential substrate concentration, and then they will also give us the mu max, Ks, and K. Okay, so to solve this question, firstly we need to write the substrate consumption during the growth, which is ds over dt equals to negative kx, and then the cell growth, which is the dx over dt equals to mu x. So we need to combine these two. So in order to combine, we can take x as subject. So when we rearrange, we will get x equals to 1 over mu times dx over dt. Okay. So, and then we will substitute x into the first equation. So we will get, and then we will integrate, and we get integrate ds equals to negative k over mu integrate dx. And then if you remember the monod equation, which describes the mu, so we can replace or substitute the monod equation into the mu in the equation that we got. So, and then we will get mu ds equals to negative k over equation, monod equation, mu integrate dx. Sorry. Okay.
Okay, so rearranging gives the equation 0 to S0 S over Ks plus S, ds equals to negative k over mu max, integral of xx xs x0 dx. Okay, so how do we rearrange this? And go back to the previous slide. We just move the s over ks plus s. We will cross multiply, but we remain the u max here. So it will be negative k over u max integral of dx. And then here will become s over ks plus s, because we, from just now, we cross multiply over here. Later we integrate both sides, which leads to, okay, when you integrate this, it will be this, and then if you integrate this, it will be like in the bracket. Okay, then the average mu can determine by dividing the specific growth rate with the total substrate in the reactor, which gives, this is the mu average, this is the specific growth rate, we integrate it over the total substrate ds. After we replace the u in the previous slide, u is the theory. Okay, u equals to u max, mu max, s over ks plus s. We replace this to the equation. Then the u will become this. But the mu max, we move outside of the integrals, it's easy for us to integrate this. So when this one will be similar with this. So when we integrate this, we'll get the one in the bracket. So we replace the one in the bracket. S0 plus Ks. Then the U max remain. And then you integrate the total substrate in the reactor, you will get S0. Okay, so therefore the new cell growth expression should be in the form of dx over dt equals to mu average x. Because in the previous slide, it was dx over dt equals to mu x. But after that, we find the mu average, so we replace the mu with the mu average. There, mu average x. Later we integrate this to find t, because the question asks what is the time. So we integrate this t to 0 dt. We cross multiply, we move the dt up. Then the mu average x, we move down. We move that side. Then after later we move out the 1 over mu average, 1 over x. So we integrate the 1 over x only. So it'll be easier for us to integrate without the mu average, because it's the power of dx. Later we integrate this and differentiate. So integrate and differentiate cancel off. So we will get t. Then everything will be in the terms of t. 1 over mu average remain the same. When we integrate 1 over x dx, get ln x s over x0.
Okay, now we need to find the value of the growth rate maximum for the cell, which is xs. So basically, to find this, we know that this equation we got from this one. After we integrate both sides, we just got this equation. And the value of this, both of this is being given by the question, which is XO is basically a growth rate initial of the cell, which is 0.08, and then this is the specific rate growth maximum of the cell, which is 0.55, and then this one is a mass of substrate over cell, which is 1.4, and this one is a concentration of the initial substrate 36, and Ks is the monad constant. Okay, and after we fill it, then we will got xs is equal to 12.604, and then we need also to find the average of the rate of the growth rate average, because if you guys refer to this equation, we have this value and you have the value, but we doesn't have this value. So basically we need to find the average. So basically this equation is so from this one. After we got this one, and then we just fill the value, okay, which is basically from the question, and we will got 0.487, and after we got the value of the specific growth rate of average, then we can get the maximum time, which is t is equal to 1 over specific average rate ln xs over xo. So basically just use the value, which is 0.487, and xs we just got from this one, 12.604, and XO is basically from the question, which is 0.08, the initial of the growth rate cell, and then we will settle it, and we will got T is equal to 10.34 hours. So that is the time maximum for the bacteria to for the maximum growth rate. This is the time.
So, before I end this presentation, I would like to give credit to 4 members of our group, okay? Because these 4 members prepared the slide for us to present. So, I would like to give credit to them, okay? So, that's all from us. Thank you.